Okie dokie. So the last video I'm going to make today in this series of super happy fun time videos. An object has initial velocity, I'm going to do question 5, 20 meters per second, moves in a straight line, acceleration is 4e to the power of minus t on 20, show that as t increases, I need a pen. It's showing up here. Alright, so I'm doing question 5 from exercise 5C3. We're looking at an acceleration function of 4e minus t on 20 meters per second squared. Show that as t increases, the object approaches a limiting velocity. Okay, well, I think we should find the velocity function then. Approaches a limiting velocity, right? So, we need to consider the velocity. It means we need to integrate the acceleration function. So velocity will come from the integral of acceleration. Now, was there any other information? An object has initial velocity of 20 meters per second. I'm going to need to know that. All right, so we also know that the velocity when time is 0 is 20 meters per second. So that's going to help me find my constant of integration, which will be in the antiderivative here. So I need to integrate 4e to the minus 120t. I'll write it like that with respect to t. So we keep our constant. 4e is its own integral, or e to the x is its own integral. Now if I was differentiating at this point, I would multiply. I'd use the chain rule idea, and I'd multiply by negative 1 on 20. But I'm not differentiating, I'm integrating. So I need to divide by negative 1 on 20, right? Which is the same as timesing by minus 20. And you guys know that. If you divide by a fraction, you flip it and times. Or tidy it up this way maybe, so that they cancel out. And you get minus 80 e minus 1/20th t, or you can just put the t in here if you like. Oh, plus a c. Forgot my c here as well. Right. Now we know that the initial velocity is 20. Okay. So using that information they gave us, let's say therefore minus 80 e to the power of 0, so I'm putting a 0 in here, plus c needs to equal 20. All right, e to the 0 is 1, so this is just minus 80, and c will therefore equal 100. If I can remember all this and write it somewhere. Here, okay, that's the one I want, isn't it? Just want to put it out the way. C was 100. I've got my full velocity function now. Minus 80e to the minus t on 20 plus 100. Okay, we've got an exponential graph here, and I think I was showing this in another video. You should be able to figure roughly what the shape is from your knowledge of the most basic exponential graph, which is this one, what we've got here, shape-wise, it will be the same as this, right? So the x values are swapping, right, ending up there, and then the y values as well, right? Because well, you know, all of our positive x's are becoming negative, and then the output is becoming negative as well. So it's effectively the y is becoming negative, and what you're going to get is this shape here. So this is your what that would look like. I'm just doing that to get the shape, right? So I know that I'm sort of getting this sort of curve, right? Now, if I consider where did we start on this graph? Well, we already know that, it's 20. I can consider where do we end up? I can see that with this more basic exponential function, the x-axis is an asymptote, but our function has been lifted up by 20 and multiplied by 80. So where's our, see ya. So where's our asymptote? Question mark. We'll have y equals, you know, or I should say velocity equals, whoa, question mark. All right, so the way we can find that is to consider, I've just got enough room here, consider when t approaches infinity. If I rewrite this function, I think, well, the velocity function is 100 minus 80 on e to the minus, not minus, I've put it into a fraction to make it clearer. So I'm dealing with the negative indices. I'm putting it into the denominator here, this power. And what I would see that as t approaches infinity, this number here is going to get very, very large. And what happens if you divide by a very large number? It's like you're saying, I don't know, I put some large value in there and this denominator equals 1 billion or something. I'm saying how many billions are there in 80? Not very many. This approaches 0, right? So you end up with just 100 left, right? Or very slightly less than 100. So what's happening is that your asymptote is 100. And I think that by drawing the graph, you're really answering the question, which I'm about to draw it properly now. Got to remember, it starts at 20, asymptote's at 100. By drawing the graph, you are showing that the velocity reaches an upper limit. Although communicating it in words can be a little bit more tricky, so I'm going to put on the asymptote. I'm not really worried about negative t values, but we'll put, because time can't be negative, so we've got velocity equaling 100. We're starting at 20, about a fifth of that space. We're coming up with that shape that we saw in a more simpler exponential. Our units, always a good idea to put your units onto the graph, especially in a test. Right, like this. So if you're drawing a graph, you're really answering the question. You could say, you could also put it into words. So I could say, what could I say? You know, if I've written out this function maybe in a way where it's easier to see, 100 minus 80 on e to the t on 20. I could say as t approaches infinity, v of t approaches 100 from below. And I suppose, you know, we could point out that this, just this bit in here, this can never be a negative number. I can never get greater than 100. But I think writing this is enough. Okay. Now, let's have a look at what the question's actually looking for. I presume there's some integral calculus. I'm doing question 5. Find the total distance traveled in the first 10 seconds of motion. Now, because velocity is always positive here, distance it is the same as displacement. Right? Now, I guess we could do it the long way. So, but remember, you have a calculator. Just find the integral. Right? You don't need to worry about any negative displacements. You can go directly to the integral from 0 to 10 of the velocity, and it will be answering that distance question because distance and displacement will be the same. So minus 80 e to the minus t on 20 plus 100 with respect to time. So if they're asking for working, we'd need to find the antiderivatives. And I need to know what 80 times 20 is. So we're keeping our constant. We're keeping our e because it's the magic function where e to the x is its own integral. Then the way my brain processes this, I think if I was differentiating, I would at this point times by the derivative of this number here, or this minus t on 20, which would be multiplying by minus 1 on 20. But I'm not doing that, I'm integrating, so I need to therefore divide. Dividing by minus 1 on 20 is the same as multiplying, but I'll write it by 20, but I'll write it like this, so you can see that. And in the 100, we want to integrate that as well, and that's easier. We need to evaluate this from 0 to 10. And I'm going to need more space. So, what we have here is 2 8s, 16 plus 2 zeros. We've got 1600e minus t on 20. We don't have to worry about any constants. 100t from 0 to 10. So that equals 1600e to the minus a half. So if I put a 10 in there, I get 10 on 20 plus 100 times 10 is 1,000. And then I need to subtract here as well. That's right. So I'm plugging zeros in at this point. Plus 100 times 0 is 0. And I can work out what that is with a calculator, but I'll leave that for you to do. I would just like to know what the answer is at this point. So calculator time, the way I'm going to do it, let's clear a bit of screen. So that's using the antiderivative if you're asked to show your working. If you're not asked to show your working, you don't need the antiderivative. You can put the velocity function that you've worked out straight into the calculator integral. So we're going from 0 to 10. Our velocity function, I think I forgot it already, 100 and I think it's a minus 80 e to the power of minus x divided 20 dx. I can't see it there, so I'm going to double check. 100 minus 80 e to the minus t on 20. 100 minus 80, yep. And we get 370, I'd probably say 0.5. If you had 3 sig figs, you'd just say 300, right? So, sorry, 370, I mean. Very close to 370 and a half, isn't it? So we could say approx 370.5 meters. But if it's 3 significant figures, which it often is, approx 370, because we had 0.4 here, that's if you're quoting 3 significant figures. You don't need to be super accurate. I don't want to see all of these decimals not required. Right? So I think that's it. If I can read underneath this, find the total distance travelled in the first 10 seconds. Yep, and that's where the question ends. So hopefully you're not finding these too difficult. 5C3 doesn't seem any harder than 5C2 to me. One of the main differences is that they're giving you information so that you can find the full velocity or full displacement equation. So when they're saying at time is 0, the velocity was 20, and I'm using that to find this constant. Okay.